Well, good morning, good afternoon, and good evening to you all, wherever in the world you may be listening from. I'm Peter Lloyd from the US Wheat Middle East and North Africa region, and on behalf of my friend and co-presenter today, Ivan Go from our South Asia regional office, and all of us in the technical team of US Wheat, we bid you a very warm welcome to this fourth session in our Creating Value for US Wheat webinar series. Today's session is entitled Flour Streaming, Putting SRC to Work. I'd like to begin with a few words of thanks. First and foremost to all of you for attending today. We really do appreciate your attendance. Secondly, to Drs. Louise Slade and Harry Levine for developing SRC and sharing it with the world. To Roy Chung for introducing me to our SRC, and also to Dr. Becky and Dr. Shunai Simsek and her team at NDSU for indulging my never-ending non-scientific questions, and also for their research and support in confirming the potential use of SRC as a tool. I'd like to make a big shout out to the wonderful QC and R&D teams in Asia with whom we have worked to realize the potential of this technology. You guys are stars. To our colleague Tariq Gahi for his patience, perseverance and testing on SRC at the Moroccan Milling School, IFIM. Before we go on, a few caveats. I am a flour miller and not a cereal scientist, so I ask your forbearance if I make any errors on the science side. It is very important to note that no milling company sets out to make bad flour. Long-term repeat business is the key to their survival. A bad flour may just be a flour which is not well suited to the product being made. We believe every stream of flour in the mill has some application for which it is ideally suited. Our challenge is to discover those applications. I should point out that in North Asia it is very common to find mills producing between 200 and 300 different functional flours for very specific end uses. Moving on now, in session 2, we learned about making cumulative attribute curves from Mark Fowler, and we built on that in session 3 with learning all about the hows and whys of the SRC test itself. Our learning objectives are 4 today. First, we want to define what we mean by streaming. Secondly, a review of how to take streaming analysis and make a cumulative SRC curve. Third, we will learn how to interpret those curves. And fourth, how to use Excel features, standard Excel features, to select streams against attributes that you choose. So what do we mean by streaming? Streaming, in the context of this presentation, refers to the selection of one or more flour streams in the mill based upon one or more attributes that correspond to functionally specific performance of flours for one or more specific end users. This is not new technology, however. It's also known as divide milling, which has been commonly used by millers around the world to produce functionally specific flours, multiple different types of functionally specific flours from a single grist. The aim of this exercise is to create as many niche products as we can, because this is where the highest margins exist in most free market environments. Until the arrival of SRC, this was only possible with very extensive R&D investment, but SRC has changed all of that. And that's why we are so excited by the technology. At the most basic level, a single attribute streaming exercise is shown here based upon cumulative ash curves, where streams up to 0.5 ash are segmented into flour 1, and those streams between 0.5 and 1% ash are segregated into flour 2. This is quite a common practice, but offers very little in the way of opportunity for niche marketed products. By comparison, Here is a multi-attribute streaming selection segregating flours into 4 different functional groupings based upon their end product performance. Obviously, this involves more conveying equipment and a more complex production regime, but offers the ability to add value to the mill streams by preparing niche market flours. It is for this reason that many mills in Asia have 5, 6, or 7 flour conveyors. Clearly, this doesn't work in all markets. There are some markets where only a straight grade, lowest cost flour is demanded, but that is not the target market for this presentation. As explained by Roy last session, individual stream data in terms of quantity is collected from the millers, giving us the weight in kilograms or pounds per hour of each stream, which is then expressed as a percentage of the feed to the first break passage in the mill. So armed with our stopwatch, our sample bags and rubber bands, we set off and collect a sample of flour from each flour stream in the mill. Generally a good idea to start at the tail end of the reduction system and move forward, then move to the tail end of the brake system and move forward. Each sample must be labelled, the weight recorded, and the bag sealed with a rubber band to prevent the ingress of moisture. That is then transferred onto a table where we calculate the stock quantity of each stream that can be calculated in 1 hour and expressed as a percentage of B1 or the feed to the mill. It is a good idea to make sure that we take enough samples that we can do all of the analytical tests, as well as have enough left for us to be able to do some finished product testing at the end. The samples are now sent to the laboratory where after 72 hours of aging they can be tested. In the case here we're going to test SRC first with lactic acid, sucrose, sodium carbonate, water and ethanol if needed, and calculate the GPI for each analysis. We're going to measure protein, moisture, ash, damaged starch, wet gluten, and if we're making cake flour, we need to get some good idea of starch viscosity. If we need to get some idea of mixing, then we should have a test like the alveograph, which is linear, to run that number. Once the results are back from the laboratory, we combine the laboratory results together with the milling analysis data into one large table of analysis. Now, I realize that you can't read this, but bear with me, it is a huge amount of data. Most of the problems I've encountered with labs have been in the process of accumulation, so please allow me a few minutes to remind us of the objectives. We're looking at the process of accumulating extraction of flour in the orange table, and at the same time accumulating the kilograms or units of an attribute in the blue table. The graph we developed shows us the growth of the accumulated attribute expressed against cumulative extraction. It is important that the attributes to be measured is ordered in ascending order of magnitude. Occasionally, when you reorder the attributes, you will see an error in the cumulative column because the formula is trying to add the cell above to the cell to the left. And if you see a hash value exclamation mark error message, it means that you're trying to add a text value, for example, the field heading, to a number. Correct this and it works just fine. In order to overcome this, I would suggest using the formula shown in the grey box here, which checks to see if the value of the cell above contains text, and if so, it only uses the cell to the left. If the cell above is a number, then it adds that value to the left to get to the accumulated value. Please use this wherever you're using accumulated values, and remember to copy it down to the bottom of the column too. While you're getting comfortable with this process, may I suggest that you copy the milling data up to and including the cumulative extraction, as well as the selected attribute column, for example, ash 14% moisture or dry basis, to a separate sheet, and work on that new sheet for your attribute curve. This avoids the issue of curves changing without warning when you work on a new chart. Put each attribute on a separate sheet and each attribute curve on its own sheet. So what happens when it goes wrong? Common problems are, more often than not, fall into one of three categories. Either we have an issue with accumulation, which you can identify with the hash value exclamation mark sign there in the table, or we don't have the attributes in ascending order, in which case we get a crazy looking graph. Alternatively, quite often, we don't select the right type of graph. We use, for most of our curves, an XY scatter chart in Excel. Using ash as an example, each flower stream is analyzed so we have a table. This is added to the milling data, which has now got cumulative percentage of B1, or cumulative yield. The table is then sorted from the lowest to the highest ash on your chosen moisture basis. Ash percentage is used to calculate the weight per hour of ash in each stream, and these too are accumulated. Cumulative weight of ash divided by cumulative weight of flour gives cumulative ash content. Easy, right? The same process is done on each of the attributes we wish. Continuing with the ash example, once we have determined cumulative extraction and cumulative ash, we can then select the two columns of cumulative extraction and cumulative ash and create a new ash curve by choosing Insert, Chart, and select the type XY scatter chart. Cumulative extraction is shown on the x-axis and cumulative ash on the y-axis. You can fine-tune the chart's appearance until you're happy with it. However, please make sure that you use a standard y-axis setting for all your charts, or you could get confused. I do frequently. These two charts are exactly the same data, but on different y scales, and this can be misleading. As you can see from the example, we have the ash curve on both dry basis and 14% moisture basis, but with different y scales. Excel now provides us the possibility to smarten up the chart by adding different elements to the chart. Simply click on the plus sign on top of the top right of the chart, and you can add all sorts of chart elements. Axes, titles, chart titles, data labels, error bars, grid lines, legends, and trend lines. These are all selected from this point. So far, so good. But where is the trend line? Trend lines are very useful for showing tendency or trends in the data. And if we can achieve a very close fit to the curve, it allows us to do some predictive maths on the curves. Trend lines are by no means necessary, but they can be very useful. To add a trend line, if needed, select Trend Line from the bottom of the Insert Elements box. You will be asked to identify the series for which you want a trend line, and in this case, we are going to use dry basis ash. Next, you will be asked to identify a type of trend line. If you are looking for a predictive regression, select one with the best fit to the curve, that is, the highest R value. I tend to use fourth-order polynomials in most milling examples. You can show a lot with trend lines. The R value is the correlation value of the trend line to the data. The higher is better. 1 is perfect. If you want to show the regression formula and correlation R values, please be sure to check the 2 boxes at the bottom of the trendline screen. And voila, here is our finished cumulative curve. So what are we going to do with that now? Well, we send it to the boss, who signs it and says thank you and puts it in his drawer, never to be seen again. Now, I certainly hope this is not the case. Here's an example of a flour protein curve on a dedicated soft wheat line. Note here that we have an excellent correlation to the trend line of 98.6%. This means on this mill, with this wheat, we can predict with 98.6% certainty the level of protein in flour using the equation. Here we have the cumulative water SRC curve. Water SRC is often referred to as the control solvent. This means that water SRC gives us the overall ability of the flour to hold water. In order to drill down further and find out which of the water-holding constituents, that is arabinoxylans, damaged starch and gluten, are contributing in what order to the overall water holding, we use the 3 other solvents, sucrose, sodium carbonate and lactic acid. Here we can see clearly the split between low and high water absorption in the flour. Remember, if you will, Roy's chart on high water and low water products. Next, we have a cumulative sucrose SRC curve, showing us the cumulative arabinoxylan content in the flour, important when we're considering what products we wish to make. Once again, Roy and Tarek's table on different products desire for water sequestration or holding water during baking. Low water sequestration is used for dry cookies or biscuits, crackers. High water sequestration is in wet products, that is cakes, and also for bread. Here we have cumulative sodium carbonate SRC, reflective of cumulative damaged starch in the flour. Once again, we refer to Roy's specifications on low damaged starch, less than 4% AACC, damaged starch in dry cookies and crackers, and high damaged starch of greater than 4 but less than 8% in bread types, and products where higher amounts of damaged starch may be desirable. Turning now to cumulative lactic acid. This indicates to us the amount of high molecular weight glutenin protein is in the flour. There is a clear distinction made between streams where we want gluten and where we do not want gluten. Lactic acid SRC is a very good indicator of gluten-forming potential in the flour. The low gluten-forming potential streams, up to about 26% extraction, are ideally suited for cake, wafer, and soft cookie use, and those streams with higher gluten-forming potential in other uses where we do not in fact want gluten to be formed. This final chart shows us the cumulative GPI values in the mill, which, as you will remember, is the lactic acid SRC divided by the sum of sodium carbonate SRC plus sucrose SRC. Perhaps more than any other measure, this shows us which portions of the mill's flour can be used for low to medium gluten forming potential, for example in cookies, cakes, wafers, and so on, and how much for higher gluten forming potential in hard biscuits, crackers, and even different bread types. I will now hand over to Ivan to work through the next part of the exercise, how to select the stream. Ivan, all yours.
Thank you, Peter, for the excellent explanation of how to process the data and using the Excel program, which the process may appear to be difficult to you, but do believe me that practice makes perfect. So now we have all the data and graphs ready. How are we going to use it? That's the point that we're going to discuss in the next presentation. You may get familiar with this SRC reference guide for soft wheat products from the last session of webinar from my colleagues, Mr. Roy Chong and Mr. Tarikahi, which I usually call this the SRC guidelines for beginner. What I wish to re-emphasize is that the range is rather wide for each type of flour. You, as a miller or end user, may discuss among each other to narrow down the range as you get familiar with the SRC test. That will ensure better stability in your flour performance. Again, the SRC value for water, sucrose, and sodium carbonate are preferred to be lower, especially with these low moisture products, cracker, cookie, and wafer. You don't want your product to be absorb extra water so that you can dry it off in the oven. In this case, water is way more expensive than any of your ingredients because you will use more electricity to dry off your products. Remember, electricity will never be cheaper than your water in most places. As you can see for the SRC lactic acid for cracker products, it can be slightly higher so that it will provide certain strength to the product, especially during laminating. Same for the SRC reference guide for hard wheat flour. This will be the opposite approach from what you see in the soft wheat flour, where we want the flour to have better water absorptions. Therefore, you will see the lactic acid is higher than 140, and also the SRC sucrose value is higher because of the water extractable arabinoxylane, or the common terms pentosan, can hold the water even after baking. This will help in prolong the fresh keeping quality of your bread. It means that your bread stirring rate will be slower. But please keep in mind that this reference guide is for high sugar and high fat formulation. So you have the data from your meals and lab, and now you have the SRC reference guide for both soft and hard wheat products. Now let us go into the section on how to process your data to find out what is the best flour blend you can get from your flour stream that you collect. Look at this table. Always remember to convert your data to 14% moisture basis. So this will allow us to compare apple to apple and not apple to orange. Also, you may consider to add another row to rename your data title in simple way or short form. So for example, moisture to M percentage, protein P percentage, and the bracket of 14 MB stand for moisture basis, which this will make us easy to see the data, and also in the next step it will also help to do the data filtration later. So next, you will need to select the row, the entire row that you create just now, and go to the Excel ribbon on top of that and click on the data, and then look for the icon of filter, and then you click on it. Once you click on this icon filter, so you are going to see such icon that appear in your row of data that you select just now. So now you can start to do the data filtration based on your desired SRC value range in relation to your product performance. But how are you going to get your SRC value range? There are two ways you can do it. One is to follow the reference guide that I mentioned earlier on for the soft wheat product and also for the hard wheat products. Or another way is that you can go to the market and then collect the flour sample. You don't simply just collect any flour sample, but to collect the best flour sample in your market, and then you run SRC on that particular flour sample to get the fingerprint, the SRC fingerprint of the flour, and then you use the value that you collected and use it as a starting point for your SRC data filtration. So for cookies and cracker, usually we are categorized into two main categories. One is a low moisture product. For both is a low moisture product, which is the moisture can be below than 2%. And then also the next category is the gluten strength. Can be either weak gluten for cookie and also slightly stronger gluten strength for cracker because of the process where it requires laminating. So standard SRC solvent actually properly classified the flour according to the broad functional classes. So the preferred functional composition of polymer can be different depending on your product needs. For example, these cookies and cracker, we want it to be low moisture. So sodium carbonate need to be low, and also your sucrose also need to be lower so that it will not hold extra water because you need to dry off your products. So this is the one of the example that I'm going to discuss for cookie flour. So for cookie flour, usually you have two desired product quality. One, the good spreadability, which is you usually referring to low glutening, so that your product will spread and without shrinkage in the oven. So glutening is referring to lactic acid. So when we want a low glutening, usually we also referring to low lactic acid. The next product quality that we are referring is your product moisture need to be lower than 2%. So in this SRC component, the two main categories that holds up the water is damaged starch and also pentosan. So in order to achieve this low moisture of 2%, we also required lower sodium carbonate SRC and lower SRC sucrose value. So you can see this parameter is considered the initial parameter that we set for the cookie flour. So you can use this range as your starting point for you to run the data filtration. Then once you already set up your range for this cookie flour, for example, your water below than 70, your sucrose, SRC sucrose below than 90, SRC sodium carbonate below than 85, and also the last one, SRC lactic acid below than 100. Then you can go to your data, and also you can click on the filter arrow for lactic acid. Let's say we're starting from the SRC lactic acid. Then you will click on this filter, and then you go to number filter. Once you click on this number filter, and then you go to this less than, you click on the less than menu, and it will pop up a window of this for you to key in the number that you want to filter. So you type in your desired value. So for example, just now we are saying that the lactic acid value need to be lower than 100. So you enter this 100 under here, and you click OK, and once you and it will automatically remove any of the SRC lactic acid that is greater than 100. It will not be shown. So those that remains is those below than 100. Then you continue to do for your sodium carbonate, for your sucrose, and usually once you get all these three set up, your water definitely will be meet the category that you are setting up. So once you have decided which stream to select, then you can proceed to blend the flour based on the ratio of the yield. Meaning to say that once you complete your selection, complete your filtration, you will end up to have the stream that meets all the parameters that you set just now. So for this case, the cookie flour we have all these streams available, and this is the yield coming from each stream. So next, we actually what you can do is that you copy this stream and the yield to another Excel file, and then you total up the yield of this chosen stream. Then we assuming that these streams are equal to 100% when the flour is blended, so the ratio for the each stream can be calculated, the stream weight in percent. So from here you will know that this stream will weight how many percent in your blend. And based on your desired flour weight needed, for example, cookie flour, you need to run the cookie spread test. You will not need too high of the flour sample for your blend. So let's say you only blend 1 kg of the sample, then you actually calculate the weight of each stream based on the flour ratio that you are getting from this stream weight. So this is an example. Once you get a sample size of each stream based on 1 kilo or 1000 gram, then you weigh your flour sample of each stream based on the weight that you calculated out, and you total up all these, you can get 1 kg of flour. So after you blend the flour, actually you are good to go to proceed with the end product testing and evaluation. So let's say if you already done your cookie spread test and you found that okay, this product, the first trial is not doesn't have a good spreadability and it doesn't achieve your needs, then you can actually go back to your data filtration that you did just now, and you change your parameter. For example, you want it to have more spread in this case, and you think that your product is too moist, then you can change your next trial. You lower your lactic acid to, let's say, below 85, and also you further reduce your SRC sucrose number to below 80. Then you reblend your flour according to the previous exercise, and then you run again your test. So this is a repeated process for you to do until you are able to blend out your desired flour quality based on your desired end product performance. So next, for the high protein product, bread. So usually bread also fall into two main category, whereas it is a high moisture product definitely, because you want the fresh keeping and the more moist eating quality. And then it's also have a different type of gluten strength needed. So for example, you need a stronger gluten strength, especially for loaf bread, because you need the volume. And for the pastry, you need medium gluten strength because you need the extensibility and also the flakiness. You don't want your product to be too hard and then less puffing. So again, this the standard SRC solvent actually properly classify the flour according to the functional classes. So you can actually based on these 4 solvents and find out what is the best, what is the numbers that you want to use for your end product performance. So for the next example is I'm going to talk about is a bread flour. Again, you need to actually spell out your desired product quality that you are going to achieve. For example, for this case, let's say I want a better volume product. So the parameter that I'm going to set that will affect the volume is lactic acid and also GPI. So I will need higher lactic acid value and high GPI. And then the next one is that I want the product to remain soft after 5 to 7 days, which is a lower stirring rate. Meaning to say that I need the bread that can hold the water even during on the shelf life. So in this case, I will need lower sodium carbonate because starch damage will not hold the water for a longer time. And I need the high XLC sucrose, which is pentosan, because this component will hold up a lot of water and it can stay in the product for longer time. So with all these desired product quality have been set up, and I will start to spell out what is the range of each SRC parameter that I want to set. So for this case, for example, I'm setting SRC sucrose more than 120, sodium carbonate below 85, lactic acid over 135, and GPI over 0.8. So you will actually run the data filtration like what you did in the example 1 on the cookie flour based on the desired parameter that you set up. Again, if you are not happy with your end product quality, you can always go back to reset your parameter and reblend the flour like you did for the example 1. For example, this is let's say you still think that your product is not moist enough and still faster, then you can further increase the sucrose to 130. Again, once you see once you get your desired product performance, then you can start to blend the flour. Based on the exercise we have gone through just now, I would like you to consider is if we can look at your cumulative curve of lactic acid and dissect the curve based on the different optimal lactic acid performance for each different types of flour. So look at this curve. We can actually now producing at least 4 different types of flour according to the lactic acid value. So for example, on the left side, your flour 1, lactic acid below 100, you can get about 7% extraction of total of 78. And for your flour 2, cookie flour, lactic acid in between 100 and 120, you can get the extraction about 13%. And then anything that in between 120 and 140, you can get your French bread flour. And anything that is above 140 lactic acid, which will take us from 45 extraction up to 78% extraction, which is optimum for this pan bread flour in terms of functionality. So this is what we meant by streaming, where we actually take the cumulative curves for lactic acid, sodium carbonate, and GPI, and then split those streams where we consider very low lactic acid component down here, flour 1 and flour 2, which is below 120, and versus those above 120. So if we take out this flour 1 and flour 2, we will end up with a superior bread flour because we have more gluten forming potential in the flour that remains in the flour. So this will require that we are just slightly different approach in measuring flour that we need and start looking at the functionality rather than whether the flour is coming from a soft or hard wheat, and also what kind of the best product can we make out of this flour based on the flour streaming using SRC as a tool. This is another typical example of the cumulative lactic acid SRC for hard wheat line. So you look at the lactic acid cumulative curve, you are able to produce at least 3 different types of flour. For instance, biscuit flour, lactic acid below 110, French type of flour, where the lactic acid is between 110 to 140, and also anything that is beyond 140 you can use it for your Asian pan bread. This is another example of the cumulative lactic acid of a soft wheat line from the soft wheat meal. We can do a different combination to produce different wafer flour, biscuit flour, cracker, and even cake flour. So there are 4 combinations here. Is whether you want to produce 3 flour or 2 flour, which is a wafer and biscuit, or even 4 flour, where you take the lowest lactic acid to do your cake flour, then your wafer flour, biscuit, and then anything that is higher lactic acid, you can blend it with your bread flour. And if not, you can do straight run for wafer and cookie flour if based on this cumulative lactic acid because it's below 100. On this slide, you will see the application effect of gluten performance index GPI compared to bread volume. We have a typical bread test done in South Asia where we have a low volume of heavy panning weight and light panning weight. In both cases, we see the GPI is an amplifier for bread volume, where a small change in volume results a big change in the GPI. And that makes this a very valuable tool for us in considering the functionality of flour. So the following slides are the streams selected from 100% soft wheat grease of a long surface mill in Asia, and the results are only for illustrative purpose only. And the selection of stream is diagram and crop year dependent. So based on the stream that we collected, this is the stream that is selected for biscuit flour, where you can see all the lactic acid is below 100, sodium carbonate also below 85, sucrose below 110, and water. And this is cake flour, where the lactic acid is in between 80 to 100 and estimated below the 4%, where your RVA is more than 3000. Then your cracker flour stream, where your lactic acid is more than 100 and is but below 115. And next one is your wafer flour, where also your lactic acid is below 100. Then you also can do the bread flour stream, where you select any of the GPI that is greater than 60, so you can actually get this 6 stream out from your soft wheat line. So look at this. All this is the unchosen stream from all the previous flour product. And what are we going to do with all this? Actually, you will be surprised that your R&D or your product development colleagues are able to produce um, a new range of potential new products from this list if they are able to find out the SRC value from each flour in your market. So don't worry, because all this price still can be used. Thank you, and I will let Peter to do the conclusion.
Thank you very much, Ivan. So, ladies and gentlemen, what we have shared with you today is going to give you more work, both in the lab and in the mill. Sorry for that, but it does open up some significant new opportunities for you to increase the end-use functionality and consistency of the flour you are making. Through this, hopefully, improve your customers' satisfaction with your product, and hopefully provide a greater value to your flour products as seen through the eyes of your customer. And through that, a higher price, or at minimum, a reduced tendency for your customers to blend your flour with other competitors' flour. Knowing more about the cumulative curves of your flour streams will enable you to optimize the full range of different products you are producing from your mill. Using SRC and streaming to split the curves can increase the functionality and performance consistency of your existing flour types in the market, as well as providing you with new opportunities for developing new, higher value products. Our aim is to enhance all three components of value: price, quality, and service, as seen through the eyes of your customers from your mill. Doing this will enhance the desirability and hopefully the price of your flour in the marketplace. We hope that you've enjoyed this session and would now ask our Senior US Wheat Officer here today to take over the question and answer session. On behalf of both Ivan and myself, thank you all for your attention today and for your valued business. We wish you every future success.